So there we go. Dimensional analysis that lets us know whether different systems are acting similar, in this case, acting compressible. But here's a question. Why did we use the speed of sound to non-dimensionalize? Why is this the relevant speed that was used to get this velocity scale? Does anyone have any thoughts about that?
Is it because it was originally considered like this barrier you couldn't cross?
Well, not really, not exactly.
Does it
So
have to
it
do
is
with
true
wave
that
propagation?
going faster is something about propagation. I heard the word propagation being murmured by somebody.
So does it have to do with the speed at which like sound is propagated through a fluid, right? And then if something moves faster than the propagation wave, you get that like cone effect rather than I'm trying to explain it. You get a cone off of a supersonic body, and that's because the waves can't keep up with like the speed of propagation through the fluid.
Yes, you are talking about a sonic boom, which we'll talk about sonic booms briefly at the end. What you're getting at is the fact that the speed of sound tells us how waves, sonic waves, propagate through the body, and that has to do with compressibility of the fluid. Okay, because the speed of sound is waves of fluctuating pressure and density. That's why you hear it, because that fluctuating pressure bangs on your eardrums. And the speed of sound is defined like this. So it comes from, so how much of a change in pressure leads to one change in density and vice versa, gives us the speed of sound, which means that the speed of sound is related to the directly related to the compressibility of the gas, how easy the gas is to compress, or the liquid also. So, okay, and it'll depend on things like the atoms and the interactions, all of that stuff.
Wait, what is the S subscript?
Oh, that means constant entropy.
Oh.
Mm-hmm. But in general, so let's say a fluid is easier to compress. That means that for a given change in pressure, you'll get a big change in density. So if a fluid is easier to compress, will it have a faster or a slower speed of sound? Based on that equation right there, I'm going to call on a random person. How about Carter Johnson? Hey, Carter.
Hello.
Hi. So based on that equation right there, will an easier to compress fluid, that means the same delta P leads to a bigger change in the density, will it have a faster or slower speed of sound?
Faster.
Okay, look at this again.
Wait, sorry, slower.
Slower, yep, exactly. Why?
Because essentially the density is on the bottom, right?
Mm-hmm.
So a smaller density means a bigger C value.
Mm-hmm. Yep. All right. So this tells us that if a fluid is easier to compress, it will have a slower speed of sound. If it's harder to compress, it will have a higher speed of sound. Basically, if it's harder to compress, the waves will propagate like, whereas if it's easier to compress, you'll get some compression rather than those waves kind of banging out against each other. Which is why, if you were to look up, the speed of sound in water is about 1,500 meters per second, whereas the speed of sound in air is about 340 meters per second. It will depend on the temperature, but it's about 340. So air is much more compressible than water, and it has a much slower speed of sound. Mara asked, does it have to do with water making things sound funky? Probably. Probably does. Yeah, I don't know exactly, but yes. And a lower speed of sound means that you'll reach Mach equals 0.3 at lower speeds, right? Which is why you can look up, the fastest submarine ever goes, and you can find the Mach number And you should find that water still just won't be compressible at those speeds. Whereas around an airplane, the air will be. Right, so this is the speed of sound for an ideal gas. Square root of KRT over the molecular weight. K is the specific heat ratio. So that's the specific heat at constant pressure over the specific heat at constant volume, which is a property that's important. It tells us something about the thermodynamics of whatever our material is. There is a table in the appendix of your book that gives K for several gases. Does that property change with temperature? It does. In our case, we're simplifying things. We're just gonna assume things are close enough to 25C that it's fine. So you can look up specific heat ratios for various gases. Dipper should have them. It should be a thing that's in Dipper, I would believe. For air, it's 1.4. It's 1.4 for any diatomic gas, so that would be nitrogen, oxygen, things like that. Will change with temperature. So, yes. Okay, MW is molecular weight. Now, sometimes people use just an M for molecular weight, but also sometimes people just use an M for Mach number. So I used MW. Nicholas asked, K is CP over CV? It is. Like that. Okay. Now, compressible flow makes the conservation of mass a more complicated problem. And this leads to some interesting behavior. So you've ever made a water rocket, you can sort of see that its thruster looks like this. It starts wide and then it goes small. Why does it look like that?
To increase the velocity of the water coming out.
Yes, to increase the velocity of the water coming out. You decrease that area, just like when you put your thumb on the hose and it gets faster, it increases the velocity of the water coming out, which, because of the change in momentum, makes the rocket fly up. Okay? But then a fueled rocket has a thruster like that. It gets wider. Why?
Because it's not relying on delta P.
We will see. We will see.
Oh no.
This is a question I have asked you. I want you to be percolating it in your minds. Okay. So the conservation of mass is just, we know the mass flow rate is constant, which means density times the volumetric flow rate is constant, which means density times the velocity times the area is constant. And this is all for sort of 1D flows. So we're going through like this. Okay. Right, so we could say,
Professor?
yes.
Is it because the two essentially fluids coming out of the two rockets are, one is compressible and one is not?
That is why. Yep. It is because out of the fueled rocket, flow is compressible, and therefore the thruster has to look like that for reasons that we will see shortly. Okay, so the change in the mass flow rate, rho VA, has to be 0. And if this were incompressible flow, that density would just be okay. And that gives us this. So the product rule, we can go out like that, can turn that into this here. And I'm going to divide everything by rho VA. And you end up with this right here. So if this were incompressible flow, that d rho over rho, that just goes away because density isn't changing, and you just end up with dV over V plus dA over A is equal to 0. which turns into V1A1 equals V2A2, just like we've always talked about. And that just says that as the area gets smaller, the velocity has to get bigger. But now, as the area gets smaller, we don't know. The velocity and the density can both change. And so how they will change depends on the thermodynamics of the situation. And you end up with a bunch of equations. Your book chapter on compressible flow, if you are interested in thermodynamics and math, read it. It's got a lot of derivations, a lot of equations in it. We have to make certain assumptions in order to do this. So flow through short nozzles, we are going to approximate this as isoentropic, which means constant entropy, and that changes various thermodynamic calculations. This means that friction losses have to be insignificant because friction is clearly going to increase entropy. Friction creates heat, which gets dissipated out. So we're assuming friction and losses are insignificant. Again, this is sort of short nozzles, things like that. We also assume no heat transfer. So we assume it's adiabatic in this case. And we end up getting that energy balance. And we combine it with some other things. I'm skipping this because y'all have not taken thermodynamics yet. And so we end up with this. This is what I wanted you to see.
And this is just for short nozzles?
Yeah, so this is for short nozzles, or when we assume isoentropic. This is for when we assume isoentropic, which is a better assumption. Like for short nozzles, we can assume this over holes. That's basically what that tank blowdown lab you did. You essentially assumed that flow out of the hole was isoentropic, and then you added like a discharge coefficient to sort of fuzz over the error of that assumption. Point is, you get this equation. Now, I want us to look at this and to think about what this means. So for subsonic flow, so Mach number is less than 1, is the ADV positive or negative? Gonna call on a person, actually Christian. Christian, hey. You here? Did you drop away? How about Sion? Hey, Sion.
Hello.
Hi. So for subsonic flow, which means the Mach number is less than 1, so we're going at slower than the speed of sound, is the ADV positive or negative?
So it would be negative.
Negative. It is negative. And what does that mean physically? If the ADV is negative, what does that mean?
As so would that mean like as a velocity? Like,
Okay, how about this? It means that if A goes down, if A gets smaller, what will happen to velocity?
the velocity is increasing?
Velocity is increasing. You said it. You said it like you were asking a question. You should be more confident because you were right. The fact that the ADV is negative means when the area goes down, gets smaller, velocity goes faster, velocity increases. And you were starting to say that too, because you said as velocity increases, area decreases, right? That's what the ADV being negative means.
And A in this case is the area of what?
The area of So this is of anything, the area of the cross-sectional area it's going through. Just like we use V1A1 is equal to V2A, true, cross-sectional area of flow. And that means that for subsonic flow, in order a nozzle trying to make the fluid go faster looks like this, okay? Because that cross-sectional area there gets smaller, which makes the velocity increase. It's just normal, it's how we expect. Velocity increases. But then what happens at sonic flow, which is when the Mach number equals 1, what happens then?
DATV is 0, so the velocity doesn't change.
So once we hit the Mach number, then you could just keep decreasing the area forever and ever, but it's not going to get any faster. And then finally, at supersonic flows, so Mach greater than 1, dA dV is what?
Positive. So that means if you increase the area, it'll actually increase the velocity.
So at supersonic flows, increasing the area increases the velocity, the opposite of a normal life. So if nozzles speed flow up and diffusers slow flow down, you have a subsonic nozzle and a subsonic diffuser that look like nozzles and diffusers we're familiar with, and you have supersonic nozzles and supersonic diffusers, which are the opposite. And that thing I would like you to conceptually understand. So to turn back to those rocket engines I showed you, you only saw half of those rocket engines. The whole thing looks like that. So and this is called a converging diverging nozzle. So at subsonic speeds, the nozzle goes in like that. So it speeds the flow up till it reaches supersonic speeds, or until it reaches sonic speeds, and then it widens out again to keep accelerating it to supersonic speeds. So that is why the rocket engine looks like that, because it is trying to get the hot gases being expelled to supersonic speeds.
Dr. Nickerson?
Yes.
So the reason for the equation before, the reason that we conventionally call 0.3 as the transition or whatever, what is that simply because it's like 0.3 and then you square it is like 0.09, and that's just kind of like below 0.3, it just doesn't change the equation from negative a over b much, or more than that?
Oh, so we're talking about how at a Mach number of 0.3, we start to treat things as compressible. It's just a rule of thumb. Nothing in particular happens at Mach of 0.3. It's just the faster it's going, the more compressible it is. And we just conventionally say that's where it's compressible enough that it's compressible. Maybe at some point someone did some calculations and said that's where we get X% error and decided that was too much. I don't know.
Okay.
Dr. Nickerson, I have a question as well.
Yes.
This is on the next slide. So I guess the one after where you showed us the rocket. So I'm a little confused about how it's constantly accelerating. Because it seems to me like if you just have one liquid in there, or like one fluid, right? Then its properties are such that it would like slow down, or like because it's like because it's compressible, like it would act a certain way and then act the opposite way instead of speeding up the whole time.
Well, it's just it is the speed of sound that does it. It's the waves. So some of the energy inside this flow is going into changing its density, right? So as it is going this way, okay, some of the energy is going into compressing that fluid. So some of it's going into speeding it up, and some of it's going into compressing it. And then it reaches Mach 1, and then as it passes out of it, the pressure is gonna expand the fluid, which actually gets you some energy out and is gonna keep on accelerating it. So the thing that makes it keep speeding up is the fact that you went past Mach 1. So all through here, the pressure and the density are all gonna be changing. I did not choose to go over all of those equations, but if you are interested, they are in here. So the pressure and the temperature and the density are all changing through all of this.
Okay, cool, thank you.
This is just talking about the velocity.
Professor?
Yes.
Do you have like a logical explanation for why it would like continue to accelerate as the area expands? Is it because it's like denser at the narrower section, and then as it goes further it expands more, or like it's returning back to its normal density and moving faster that way?
It will be getting more dense there. So we'll be getting more dense this way. In fact, let me actually look up what the actual equation is, and I will tell you.
Just like the second half of the thruster, because I'm still just conceptually trying to understand it.
Okay. Well, the actual explanation. Okay, so actually let's look back at here. Remember this came ultimately from using this guy right here. So there's a certain amount of energy that can go in between the pressure and the density and the velocity, right? So if the velocity gets faster, then the density should go down. The pressure should go down and the density should go down. And if the velocity gets slower, then the opposite. And so what that means is that it should actually be getting less dense as it's going through there. Okay. As I said, there's actual equations. It's hard to explain without bringing in like enthalpy and things like that, which is why I feel, I feel like the best answer is just to say that once you put in the way that the pressure and the density and the velocity all sort of trade energy between each other, because energy can go into compressing or expanding the gas, and you put it together, this is the relationship you get.
Dr. Nickerson?
Yeah.
Would it be an okay way for now to conceptually think about it like the gas that has been basically over compressed to this point, like because now it's going supersonic, when you give it more room to expand, it's almost like a spring doesn't have room to expand, and then it expands and that gives it more velocity, kind of a thing?
Sort of.
Like,
because it is true that what is happening here is that the density is expanding, which an expanding gas does work. It provides energy, right? Okay, so the expanding gas, you can almost think of that as, in this part, the expanding gas is pushing it faster.
Yeah, okay.
That's a way to think about it. As I said, I wanted to find the exact equation of the pressure because all of that is changing through all of that there. But what I wanted to talk to you about was choked flow. So you learned about choked flow in that lab you did, right? So what is choked flow?
Isn't it basically like it reaches a maximum flow through that size of nozzle or orifice?
Yes, that is it. Choked flow is when it reaches a maximum velocity. And why does it reach a maximum velocity? Well, if we imagine a nozzle like this, as we said, it keeps getting faster and faster and faster, and now it's at Mach 1. So what will the next one be? What will its Mach number be in the next step?
1.
1. It's Mach 1. Okay. In order to get it faster than that, you would have to start converging, which, as I said, we could say as it lets the density of the gas expand. Let's say that. We would have to converge out like that, so the density of the gas would start expanding. That's what we would have to do in order to accelerate beyond that. So that means that we have reached a maximum velocity. That's choked flow. Okay, and the bigger the delta P you have between here and here, the more likely the flow is to choke.
Professor?
Yeah.
So if it was shaped more like the rocket thruster, so it had an expanding area, it would go faster?
Yep, it could keep going faster.
Cool.
Yep, that's how you accelerate stuff from subsonic to supersonic speeds.
But wasn't it supposed to be that the dAdV is 0 when you're at Mach 1? So like, to me, it seems like you should be able to change the area and still have no effect.
Yes, it is, but that's just sort of how derivatives go. So it's like that's when the minimum is. That's sort of how derivatives work.
Okay.
Okay.
So, Professor, is the key that it's expanding gradually? Because I guess technically the choke flow nozzle would be coming out into the atmosphere. So it is expanding in the area, but it's just like infinite, essentially.
Yeah, that is probably the key, that it comes out and expands gradually. Because you're right. If it was just like this, it is expanding out here, but it doesn't do anything. So it probably is the key that it's expanding gradually. I don't know if there's some, probably aerospace engineers know exactly what the angle has to be to sort of coax it along. I do not know that, but
you'd have to be a rocket scientist.
You probably have to be a rocket scientist. Yep.
Is this what things like your lawnmower are referring to when you put on the choke to start the engine?
I doubt it. I doubt it gets compressible.
I don't think so. The choke basically just changes the gasoline to air mixture.
Yeah. And so a gasoline engine has some superheated gas in it, right? You burn the gas and it creates this hot air full of combustion products that you then squeeze, and then like you burn the gas and you squeeze it, and then it creates all of this hot gas which pushes back, right? And that turns whatever the thing is, and then the engine goes. So probably gas gets a little bit compressible inside a gasoline engine, because probably, I would bet. I don't think that you could get choke flow in there, but I don't think that's what that's referring to. Okay. So, okay, flow can also choke through an orifice, like with this tank. So this is like that tank problem you did. And there's a general rule of thumb for deciding whether a flow out of this tank orifice is compressible. Well, the actual rule of thumb is if the pressure is about twice atmospheric pressure, it will come out choked. And you can check it with that. And then this is the mass flow rate, assuming that there's no entropy and nothing is lost to friction. And this equation you actually used in that lab, I believe. So if you have some tank that's pressure, whatever, this is what, and it's high enough pressure that flow out of it is going to be choked. This will be the initial mass flow rate. And then what will happen over time?
It'll decrease.
It'll decrease because the pressure in the tank is going to decrease, right? You're letting stuff out of the tank. The pressure in the tank will decrease. The temperature in the tank will also change. Just out of curiosity, does anyone remember how the pressure and the temperature in the tank changes? That lab tells you in the description, but I don't know whether you haven't taken thermo yet, so it might not be as.
I think for that lab, we ended up assuming that it was an isothermal process.
Yeah.
And so the temperature didn't change much.
You did one assuming it was isothermal, so you could do the math, and then you did another one assuming it was adiabatic. So if it's adiabatic, what happens to the temperature?
It's really hot.
It should get colder.
Oh, sheesh. Okay, never mind.
Yeah. But there, because the density goes down, it should get colder, I believe, if I'm remembering this correctly. But the pressure inside definitely drops. You can assume it's isothermal, which you did for that lab so that you could do the calculus. Questions I'm going to ask you are going to be questions like air in a tire is maintained at a pressure of 20 kilopascal gauge or 220 kilopascals gauge. Atmospheric pressure is 94 kilopascals. That's a typo. Air in the tire is at the ambient temperature of 25 degrees C. A puncture creates a 4 millimeter diameter hole in the tire. Approximate the initial mass flow rate through this leak. So I'm going to let y'all do that. Can give you like 2 minutes. Let me know if you have an answer. Well, first check whether it's choked, right? So first check whether it's choked. And if it's choked, you can find the answer using the equation that I showed you.
What do we assume that K is in this case again?
Okay, so this is air. Is at 25 degrees. K is equal to 1.4. And often you will take K for air to be 1.4, even if it isn't exactly at 25. It's just, well, just like we often just take the density of water to be 1,000 kilograms per meter cubed when we're doing problems, right? That's even if it's not at the exact temperature, where that's true. What's Mach number for choked? So if it's a choked flow, the Mach number is, actually, does someone else want to answer that?
It should be 1, right?
It should be 1. Choked flow means it gets to the speed of sound and then it can't go any faster. So it gets to sonic flow, Mach number will be 1. someone calculate this?
I got 178.
178. Okay, so that means that the absolute pressure inside the tank is well over that. We can assume it's going to, or inside the tire, it's well over that. We can assume it's going to be choked going out. So now just plug it on in. Okay, molecular weight of air, I usually use 28 grams per mole. That's what I usually use, but we can Google it. Weight of air. 29 grams per mole. The R that you use, well, if we're using SI units, then we should use 8.314 joules per mole Kelvin. So if we're using SI units, molecular weight is in moles. That's what we should do. And of course, what pressure? So you're using the pressure of the tank in that mass flow rate equation. Do you use gauge pressure or absolute pressure?
Absolute.
Absolute pressure. Whenever we're doing sort of thermodynamic stuff, whenever we're talking about PV equals nRT type deals, use absolute pressure.
And that pressure of the tank equation, that's also absolute.
Yep. Yep. Well, because the gauge pressure is, it's all, if the gauge pressure is always going to be over, more than the atmospheric pressure, right? So absolute pressure, we're talking about absolute pressure in both of these. So if the gauge pressure is greater than the then the absolute pressure will be too. But yes, that's what this is for. So someone tell me what you get when you plugged everything in. Yes?
So I got like 3.57, but I don't know what the units would be since I don't know if it's grams or kilograms.
Okay, so if you did this, in order to make everything work out, this gas constant is joules, which has kilogram in it. Joules has kilogram in it. So in order to make these units work, you have to convert these grams into kilograms. Otherwise, it will be wrong. Or I suppose, let's see. Yeah, in order to make this work, you got to make that be kilograms. And then pressure also has kilograms in it. If you're going to make that be pascals, if pressure is in pascals and R is in joules, then in order to make everything work, the molecular weight has to be in kilograms. I got a few people got 9.24 grams per second. Okay, we're gonna assume that's true for now. Double check your stuff. So that's the sort of question I would ask us is get me an initial mass flow rate for choked flow.
Dr. Nickerson,
Okay, yes?
I'm still confused how we know this is choked flow.
Well, that is why we did this first. So this rule just tells us there are some more complicated equations behind it, but this rule just tells us that the pressure difference is so big that flow will be choked.
Oh, so we checked to see if the tank was greater than the right-hand side of that equation.
Okay. And all that's happening there is a really big pressure difference accelerates the flow really, really fast until it gets to sonic speeds. And eventually, when the pressure in the tank is low enough, it will slow. It's going to keep going slower, 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 slower until it drops to subsonic speed and it's not choked anymore. Choked speed is at its maximum speed. Yes?
I got a quick question.
Mm-hmm.
When we're doing this, we do, so I just looked at the answer that I got, and I'm seeing either like 9,241 or 9.241. And that all depends on whether I use the number of kilopascals or the number of pascals.
Well, yes, because look, the pressure is right here, right? So if you use kilopascals instead of pascals, that's a different.
That'll give me kilograms as an answer then?
No, because pascals go with kilograms. 1 pascal is equal to 1 kilogram times meter per second squared. Mass times acceleration is force over meter squared. That is 1 pascal. So if you put in pascals there, you should get kilograms out. If you put in kilopascals there, you should get 1,000 times that, which is like a megagram or something.
Okay. In that case, then I'm still getting 9 kilograms, and most people are getting 9 grams. Do you know what could be causing that?
Probably. So again, in order to make all of these units match, you want to make sure it is kilograms here. So you want to turn molecular weight into kilograms per mole. Kilograms per mole. And then K is unitless. You want this to be pascals, not kilopascals. And you want this to be 8.314 joules per mole Kelvin, not kilojoules. So if you keep all of those right, it should come out as kilograms. So everyone should check and make sure they did all of those in the correct units. All right, there we go. Okay, so she loves compressible. So compressible flow is actually really interesting. And I had to make some choices about how much I was gonna talk about, which maybe it led us into a bit where, I don't know, maybe that was a mistake, because then some of you were like, why is this happening? Because I skipped a bunch of the steps. There is a lot of different situations in compressible flow. We only talked about isentropic flow. And on Wednesday, we're going to talk about what happens when you have a pipe with friction, which means that there's entropy, which means other stuff, right? I will post the recording on this. Conceptually, I want you to remember that flow gets choked when it gets to sonic speeds. I want you to remember that the speed of sound is related to how compressible something is. I want you to remember that how the supersonic nozzles work. That's what I want you to remember.
Thank you. See ya.
Thank you. See ya.